Okay, here we go. Good evening, everybody, and welcome to the IEEE EMC Society meeting, the Southeastern Michigan chapter. My name is Scott Lytle. I'm the chapter chairperson here for the IEEE in Southeastern Michigan, and I welcome you all to our meeting this evening. Thank you for attending. This evening's meeting, at the very end of it, we're going to have 3 door prizes provided by KGS. So we're going to have a $25, $50, and $75 door prize. You must be present for this meeting to win. I have generated a list of random numbers, courtesy of Google. So I will match the random numbers to the roster, and we will go down the roster until we have the 3 winners. And sometimes that can take a while because we have maybe 50% of the people here that actually signed up for the meeting. So that will be at the very end. And we are recording the meeting this evening. And when I get it back from the cloud from Zoom, I will upload the meeting to YouTube, and I'll send out the link to all the people who sign up for this meeting. You can also stumble across it on YouTube, but you know, that could be a pretty long shot there. So it's probably better to get the link. This evening, we're going to have 2 different speakers. But I will read the biography that I have, but I'm understanding that he is not one of the speakers, but he is one of the contributors to the presentation. So at this time, can everyone please mute your microphones and mute your cameras so we have enough bandwidth for the presenter. And at the very end, I'll have you open your microphones back up so we can ask questions and so forth. So this evening's meeting is put together by KGS. Hideo Yumi, I have his biography, which I'll read momentarily here, but we're going to have Lynn and Kyoko actually doing our presentation. The topic this evening, we're going to cover some EMI fundamentals and EMC filtering, along with some application images that we worked out in the past, we being KGS. We're going to have some practical information rather than just theoretical data. Mr. Hideo Yumi works for Kitagawa Industries, KGS, for over 30 years. 3 years ago, he was assigned to manage the operation in the United States as general manager and president of Kitagawa Industries America. Since joining KGS, he has been involved in the development of EMC-related products and has many patents, especially in the field of surface mount SMT, onboard grounding contacts. Oh, no. Mr. Yumi, thank you. I lost my place here. Works with customers to develop practical measures to solve problems. His passion is to incorporate customer needs and new design trends into the product development. So our first speaker this evening will be Lynn Chung. Lynn, go ahead.
Hi, well, thank you for giving KGS a chance to present the seminar at the IEEE meeting. So a little bit about myself. I work for KGS for almost 6 years, and I'm in the business development team. We work to support the customers, you know, with the sample for testing and provide any technical support that they needed. I think EMC is very interesting, and I love learning about it from every engineers and customer that I work with. Yeah. Kyoko, do you want to introduce yourself or?
Yes. So hi, I'm Kyoko. I'm the business development manager at KGS America. I've been with the company since 2013, so a little over 8 years now. And yeah, we have the pleasure of actually doing this seminar with you guys. I think this is probably our 2nd time, but it's actually the first time for myself and for Lynn. So thank you very much for having us.
Kyoko, can you
Yes.
Can you back to camera and take off mask?
I'm sorry, I have
Yes.
actually another person in the room, so we're required to wear masks right now. I'm sorry about that.
All right, I take shot.
Okay.
Thank you.
Mm-hmm.
Okay. So I think let's go ahead and get started. The topics we will be covering today, including EMC fundamental and filtering. We will discuss the possible techniques which you can try, as well as what type of component solutions you may want to consider. So to suppress EMI, there's a large product range of the EMC components. So there are a couple examples. There are ferrite core for the filterings, there are gasket for shielding, there's springs contact for the grounding, and these are just a few examples. But in generals, we provide a total support of the your EMC requirements. So as an example, we would like to show a circuitry on the PC board assembly. It is a simple circuitry with a 16 megahertz clock device. There is a light emitting diode for confirmations of operations, which is blinking every second. The wire is connected to the ground, which should be a reference voltage point with a zero potential. The purpose of this experiment is that the wire is used as an antenna for radiating high frequency energy. But as you can see, the wire connected to the ground is radiating the EMI, which is to say the ground is becoming antenna. So after we discuss all the filtering technique, we will come back and discuss the solutions for this example. So this is an example of an actual test that we ran. So when using the above equation and working backwards, you can see that even a small amount of power, in this example, 35 microampere, can cause a device to fail more than 5 times the Class A limit for CISPR. So if a simple device like this can fail, a more complex device has a higher chance of failing. So EMC is about being able to control the flow of the power, and this presentations will show certain examples and methods to solve the EMI related issues. So today we'll cover the fundamental of the filtering part. Ferrite cores are very standard and common product used as EMC solutions. You may think it is not necessarily to go into details of how the ferrites are used. Typically, EMC problems are solved at the last minute and not really considered during the design phase. So the point of this presentation is to give you some tips to optimize your ferrite selection and usage. Because there's little time to evaluate the effects, we would like to share with you the information from a manufacturer point of view and from frequently asked questions from our customers. So how is a ferrite core effectively against unwanted signal noise? When electric currents flows on a cable, magnetic field is generated. Magnetic flux inside ferrite core is reduced by the magnetic loss of the ferrite, and as a result, flowing noise current in the lines is reduced. It is these opposing forces which create resistance, and this resistance generates heat. One of the objects to convert energy to heat is a resistor, but resistance is generally constant. 100 ohm resistor should show 100 ohm for both of direct current and 100 megahertz signal. Ferrite cores show the similar characteristic of resistance, but vary with frequencies. So for example, a ferrite can have 0 ohm for direct current, 1 ohm for 1 megahertz signal, or 100 ohms for 100 megahertz. So ferrites can be used as a common mode chokes where they have no influence to signal and only affect common mode noise. So these graphs show the initial test measurement. The frequency range show is 30 megahertz to 1 gigahertz. Now let's try attaching a ferrite core to the cable. We attach a ferrite core to the cable with 1 turn. On this graph, you can see that there was some improvement from 100 megahertz to 700 megahertz from the initial level. The noise was converted to heat energies by the ferrite core. We will discuss how the ferrite core can be used effectively based on these 3 questions, which we are often asked by our customers. Number 1 is the shape factors. Number 2 is the placement. Number 3 is the numbers of turns. The picture shows the experimental setup which we used earlier. We used this setup to test these 3 questions. The ferrite core is attached here on the cable. First, we examined how changing the size and shape of a ferrite affect the performance. Second, we try placing the ferrite on different locations on the cable, such close to, some distance from, and far from the connector. Finally, we test what would happen when the cable is turned on the core multiple times. So first, we will examine how size and shape affects. Many people think that the more ferrite volume, the better it will work. However, we find this is not necessarily the case. Shape factors refer to the value when you divided the area of the cross sections of the ferrite core by its mid-diameter, and that is the inner and outer circumference, also known as the magnetic path length. Although this is commonly known, the effectiveness depends on the shape factor of the ferrite core, as long as the material remains the same. So we randomly choosing 4 frequency points to demonstrate the effectiveness of the ferrite core by using the shape factor. These frequencies are 120 megahertz, 250 megahertz, 320 megahertz, and 528 megahertz, which correspond to the circle, triangle, square, and diamond respectively. So these 4 frequencies are shown on this graph without any ferrite core attached. We will call this the initial status. And this is the result with 1 ferrite core attached to the cable. And you can see that there's a decrease in noise. The red dotted line indicated the initial noise level. We are comparing the shape factors and the noise suppressions of 5 different ferrites at different frequencies point. The x-axis shows the shape factors, while the y-axis shows the reductions of noise from the initial data to suppressed level. We use ferrites with these shape factors. And these are the results of different shape factors. We connected the points for all shape factors to clearly show the positive correlations between the shape factors and the noise reduction level. The bigger the shape factor, the greater the noise suppressions. If you want to increase the shape factor without changing the magnetic path length, simply increase the length of the ferrite, which increase the section area. Now let's take a closer look at the data on this graph. You may notice that the degree of suppressions differ depending on the frequencies. The greater effects was for 320 megahertz, which is the square symbol, and the lowest effect was for the 250 megahertz, the triangle symbol. And here is a general impedance graph of a ferrite core. So we typically rely on the impedance characteristic to determine the performance of a ferrite. And in general, lower frequencies level have lower impedance and higher frequencies level have higher impedance. And again, in our experiment, the effects of noise suppressions was smallest for 256 megahertz and highest for 320 megahertz. The suppressions angle increase in order from the lowest to the highest, which is 256 megahertz, 128 megahertz, 528 megahertz, and 320 megahertz. This is different from what we would expect from the impedance characteristics. The lowest suppression should be for 128 megahertz, and the largest should be the 528 megahertz. And if we try converting our test data into an impedance graph, this is how it would look based on our test data. And if the impedance characteristics were to look like this graph, our measurements data would be supported. However, the impedance curve is more like this. And why doesn't the test data match the regular impedance curve? And we will explain this with our next questions. The locations of the ferrite on the cable. We will show there's a difference in noise suppressions depending on where the ferrite core is attached along the cable. As you may know, both common mode and differential mode currents are made up of a combinations of different wave patterns. Various frequency signals are flowing through the cable at the same time in a sine curve. So for example, let's say that there are 2 types of frequencies wave pattern flowing through one cable, as indicated as A and B, and we attach a ferrite core at one position. So in case A, the ferrite core would be attached at the antinode of the wave. That is basically the noise current. And in case B, the ferrite core would be attached at the node and that is the point of the zero potential of the wave patterns. So the effectiveness of the ferrite core will differ depending on which point on the wave the ferrite is attached. And this is why the previous during the shape factor test does not match the general impedance curve. The ferrite was probably not placed at the antinode for the 256 megahertz and the 528 megahertz. However, we cannot see the antinode of the frequencies or detect its locations. Even though the waves are not visible, you can slide the ferrite core along the cable to find its best location. So please take a look at the graph on the right. The y-axis indicated the noise suppressions, while the x-axis indicate the numbers of wave. Think of the number of wave as a frequency. We placed the ferrite core at two different locations, one 50 centimeter from the end and another 60 centimeter from the same point. The results are indicated at orange and blue lines respectively. You will notice that there was a greater effect when the core was attached to the antinodes of the wave and the least effective at the node. There is no specific locations for the ferrite core that is considered the most suitable across the board for all frequencies. However, there may be a location which will work better for certain problematic frequencies. So the frequencies with the highest level of radiated noise is where we wanted to suppress the most. The location that affects this frequency the most can be said to be the most suitable locations to attach the ferrite core. So in this example, we would like to target the frequencies around the 128 megahertz. The effects varies when we move the attached ferrite core along the cable. By doing so, we will be able to find the most suitable locations for the core. However, there may be mechanical or design constraints which could affect where the core can be placed. This situation should be taken into consideration as well. And now we will discuss whether turning the cable multiple times through the ferrite is a good option. The number of turns is defined as the numbers of times that the cable or wire pass through the inside of a ferrite. This photo shows 3 turns because the cable is passing through the ferrite 3 times. The impedance level of a ferrite will be increased the more time a cable is turned through a ferrite core. The increase is proportional to the square of the number of turns made through the core, as shown in the formula n to the square. This means that if you do 2 turns, the increase will be 4 times greater than 1 turn, and the effect is like placing 4 ferrites on the cable. If you make 3 turns like in the picture, the increase will be 9 times greater. This is the same effects that placing 9 ferrite core. We tested with 3 turns, and this graph shows the test results. Turns can have a very powerful effects for lower frequencies, as you can see here. Basically, the noise level are kind of reduced. However, it is not as effective for frequencies over 200 megahertz. In this test, you can see the noise emissions increase at higher frequencies. And why does this happen? The reasons can be explained in this simple graph image on the right. As an example, we are taking a look at the equivalent circuits of a cable with a ferrite attached to understand why the noise increase at higher frequencies. There are 2 pathways that the current could pass through, the inductance pathway or the capacitance pathway. On the impedance versus frequencies graph, there is a typical inductance line for 1 turn, shown by the aqua color dotted line. And after 3 turns, the impedance level is increased 9 times, as we discussed in the previous slide. However, when you increase the numbers of turns, you also increase the stray capacitance between the cable inside the ferrite. Basically, 1 turn, it's for the blue color, and 3 turns are the red on the left image. As the stray capacitance between the cables is increased, the impedance level decreased the capacitance pathway. The impedance curve follows the path of the lowest impedance. So for 1 turn, the cutoff frequency is at a higher frequency, frequencies, and the cutoff frequency moves to a lower frequencies when the cable is turned 3 times. This means that when you increase the number of turns, the impedance decreases for higher frequencies. We can show this in another way in this slide. So the top graph is the initial state and the bottom graph shows the ferrite effects after 3 turns. The blue line is the impedance curve of the ferrite with 1 turn. And the red line is the impedance curve with 3 turns. With 3 turns, the impedance at lower frequency is much higher than with just 1 turn. However, the impedance at higher frequency is lower due to stray capacitance. When suppressing noise over 200 megahertz, turning the cable multiple times may not be the best solution. It may even increase the noise level. It would be better to focus on increasing the shade factors, and this can be done by using a ferrite with a large shade factors or using multiple ferrite cores on the cable. And for lower frequency, which is 200 megahertz and below, turning the cable would greatly increase the impedance of the ferrite. So now we're gonna talk about the solutions for common mode noise and inverters. Inverters are used in various devices. As the device becomes smaller, they are designed with higher performance and energy saving features. Noise generated from inverters, which can radiate from the device and cause malfunctions. First, we will review common and normal mode noise route and the terminal voltage. Then we will discuss and to show you the noise current that can be identified by visualizing it using a current probe in order to help you assess the concept of the noise current. I will be conducting these information into the best applications of the ferrite core by utilizing the concept we have obtained. So in order to control the noise, we need to know which noise mode exists on the cable, either is common mode or differential mode. So in terms of the transmitted noise from the power line, normal mode noise generated at the EUT and is transmitted through the lifeline to the LSIN, and then it returns to the EUT through the neutral line. For common mode noise, there are 2 types. Common mode number 1 is shown as the solid red lines. This flow in the same directions on the L and N lines to the LSIN, and it returns via the ground line. For common mode number 2, which is shown in the dotted pink lines, this flow in the same directions on the L and G lines to the LSIN and returns through floating capacitance as a distance. We know these common and normal mode noise exits, and next we will show you how to identify them. So the following graphs are the test data that we obtained at our EMC center using an LSIN and spectrum analyzer. In these tests, the EUT is a washing machine with an inverter. In this graph, we tested the L lines only, measuring the noise from 150 kilohertz to 30 megahertz. This graph is showing that the washing machine is not in compliance because we remove all the noise filtering components to run this experiment. As purchased, this machine satisfies all compliance standards. In order to identify the noise current, we use a current probe to confirm the noise route. The current probe is used to detect the magnetic field on the power line and convert the strength to a current value. So the noise current can be easily measured. We attach the probe on the L, on N, and then on LN together to see the difference among the noise level. All of the curve on the graph looks very similar to the initial status from the previous slide. If we take a closer look at the result, if L and N only had normal mode current, such as the power current, opposing magnetic fields cancel each other out. And if this were the case, the probe would show a lower level on the graph. However, the L and N lines are clamped together. The graphs still show high noise currents, which mean that the magnetic fields are not canceled out. The data show that the currents on the LN line together is 6 dB higher than the L and N line separately. The current level in dB is calculated by the equations of 20 log parenthesis x when there are multiple currents in this example. And when this is plugged into the equation, the result is an increase of plus 6 dB. The equation supported the measurements from the probe experiment. Therefore, we understand that the L and N lines have currents running in the same directions. Although we don't know which directions, we can assume that the current is coming from the EUT and returning on the ground line. And this is the common mode number 1 route that we have explained it earlier. Now we're going to compare the noise on the L and N lines to the ground line. When placing a probe on the ground line, we see that there are similar measurements as the LN. From this, we can infer that the noise is taking its returns route via the ground to the EUT for common mode number 1. Next, we clamp all 3 lines, the L, N, G together and measure the current. We presume that the common mode noise on LN and G would be canceled out, and the reading should be very low. When we look at the result, as expected, there was a drop in the noise current, except for at about 12 megahertz. This noise at 12 megahertz is actually the common mode number 2, which is running in the same directions on all 3 lines, L, N, and G, and is returning through the earth ground. Next, we will show the suppressions level of common mode number 2 using ferrite. We will be using reference data without any EMC components. According to this graph, we will need to focus on 2 parametric frequencies range, below 1 megahertz and at 12 megahertz. We showed it in the previous slide that common mode number 1 is dominant below 1 megahertz, and common mode number 2 is dominant at 12 megahertz. First, we will focus on the noise below 1 megahertz. We will use a ferrite core that has a high impedance below the 1 megahertz. As we know, the common mode number 1 is flowing on the L and N lines and returning on the ground line. When we place a ferrite core on the L and N lines to filter out this noise, and we see that there is a significant improvement in the result, which is showing on the purple line. Alternatively, because we know that the noise returns on the ground line, we can place a ferrite core just on the ground line itself, which is showing on the green line. At about 1 megahertz, placing a ferrite core on the L and N lines together is more effective than placing a core on the ground lines alone. But since we are focusing below 1 megahertz for this test, they are about equal in performance. Next, we place the ferrite on the L and N line and on the G line for the comparisons. As you can see, there is a dramatic reduction in noise from 200 kilohertz to 1 megahertz, and we are below the AV limited line. Only at about 150 kilohertz, there is still a noise issues, but at above 1 megahertz, the noise has increased. This is because a ferrite is attached to the ground line. The dip in the noise for the L and N lines was probably because the noise found another path. So for instance, if there was a metal plate near the inverters or cable. And at around 12 megahertz, common mode number 2 is also reduced because each of the L, N, and G is filtered by the ferrite core. Here we will take a closer look at the noise around 150 kilohertz. Again, using the current probe, we measure the noise from the L and N lines, but this time we will detect the normal mode noise. Before, we clamp both L and N lines together to measure the common mode. This time, the L and N lines are inserted from the opposite directions into the current probe. This will cancel out common mode noise, and we will be able to measure normal mode noise only. Measuring the normal mode noise alone, you will see there is a substantial noise around 150 kilohertz. It is almost equivalent to the level we saw in the common mode noise test. So this is to say, in addition to common mode noise suppressions, we also need to suppress the normal mode noise. We attach one of the ferrite core the same way we use the current probe, as indicated as in the previous slide, basically by inserting the L line in the opposite directions. With this attachment method, the 150 kilohertz noise dropped below the AV limited line. As we previously mentioned, turning a cable through a ferrite increased impedance by the square of the number of turns. However, the magnetic saturation should be kept in mind because the AC current is still being filtered as opposed to only the signal noise. If magnetic saturations occurs, even if you increase the number of turns, the noise may increase instead of decrease. So in our experiments, we inserted the cable from the opposite end for normal mode suppressions, but in mass production, this is very cumbersome. A common way of solving this issue is to attach one ferrite on each line to suppress both common mode and normal mode noise. The light blue is the result from our normal mode experiment, and the purple is from this simple attachment method. In general, the suppression level is not as good. The reasons could be that there are common mode noise in both L and N in the same directions. The number of turns is essentially reduced by half. Due to the lower due to lower impedance, the suppressions may be less. In order to have the same level of suppressions of normal modes at the light blue result, adding turns around the ferrite may help. In the event a ferrite cannot be attached to the ground, the ferrite on the L end should have more turns. Next, we will cover how different ferrite material will affect suppressions level when turned 7 times. Each ferrite materials target at different frequencies. So we have the pink graph, which is for the TRMX series. It is targeting below 500 kilohertz. The red graph is for the frequencies 500 kilohertz to 5 megahertz. And the yellow graph is for the frequencies above 10 megahertz. Our suppression test data on the wash machines is reflected as the impedance graph for each ferrite material. So in the third graph, yellow line, the GTR ferrite, which is the high frequency ferrite core, has excellent effective around the 12 megahertz. However, the noise level get worse between the 150 kilohertz to the 500 kilohertz. And one reason for this could be that the resonance frequency has shifted due to the insertions of the ferrite. We recommend choosing the ferrite material based on your target frequency range to effectively reduce the noise. In our last test, we wanted to test one of the most frequent asked questions from our customers, whether they can combine ferrite cores made of different materials to target or cover a wider range of the frequencies. We did these experiments where there are low frequencies core, middle range frequency core, and high frequencies range core. And first we combined the low and the mid frequencies. It is effect up to 1 megahertz, but not good around the 15 megahertz. Then we combined the low plus the high frequencies core. It is good overall, but the lower range deteriorates. And lastly, we combine the middle and the high frequency range. It is effective around 15 megahertz, but the lower range sees an increase in noise. What this test is showing is that you cannot get the best out of both types. It is more like an average of the two cores. So based on what we have talked about, we would like to point out a few key points for you to remember. Measure the noise current on each line to determine the most problematic noise frequencies. Focus on minimizing the highest peak. Choose a suitable ferrite material for the specific target frequencies. Attach a ferrite to the lines for a specific type of noise. Either it's a common mode number 1, common mode number 2, or the combinations of the both common mode noise or the normal mode noise. Consider magnetic saturation could occur when suppressing normal mode noise. And now next, we will discuss the current application node and how ferrite will use to solve possible interference issues affecting the radio and issues caused by the battery voltage monitor unit. So these wire harnesses are used high frequency ferrite core to fill out any outside noise from entering into the harness and affecting the FM radio band. These are used for immunity. And this is where they're using the ferrite core to solve the issues for the on the battery side. This is another wire harness application using our off-the-shelf ferrite for the for the AM frequency band for filtering purpose. This is the view of the inverter, and you can see that our ferrite core, it's where they were attached in that orange cable there. This is also the inside of the inverter. It looks like they were using the ferrite core, which is around that 10 to 20 kilohertz. And it's used to help to filter out the noise in that frequency range. And there are also the plastic component that where they can help to do the cable management. Here you can see a cable tie was used to hold the ferrites in place. The casing of this ferrite was custom made to hold on to the cable ties. And this cable ties is a type of a snap mount, which is mounted onto the metal clip below. And for this one, by inserting the ferrite core on the cable of the voltage monitor sensor, you can dramatically improve the immunity of the voltage monitor unit. And special ferrite core for high frequency type should be used for effective result in this case. This is a bus bar for a hybrid vehicle that connected the battery pack to the inverter. There were some low frequency noise issues during the recharge phase. So a custom low frequency ferrite was made to fit the bar and the plastic enclosure to hold everything together. This allowed for the noise to be filtered out and keep the ferrite from moving and making any noise due to vibration. This is an off-the-shelf ferrite for the low frequency noise, but the plastic enclosure was made for the customers according to the customer requirement. They wanted to keep the cable flexible while not allowing the ferrite to move down the line. We therefore built a special case with the legs to hold onto the cable while still allowing it to remain flexible. And this is an example of a hybrid vehicle that is using a braid mesh as a connector from the inverter to the battery. This allows for the cable to remain flexible while reducing the impedance when compared to the performance of a solid wire. So in general, basically when choosing the ferrite to target the parametric frequency, it is important to choose the right material that can help to target your parametric frequencies. And there are different selections for it that will help to target the low frequency range, which is from the 150 kilohertz to 30 megahertz. They're also in the middle range, which is from around 3 to 50 megahertz, and also for the high frequency, which is from the 30 megahertz and above. There are also other component solutions as well. So other than the filterings, there are also shielding and grounding technique that can be considered depending on your applications and where the noise problem is. And maybe it's needed to be a combined solutions of these three to target or to help to reduce the EMI noise. To help combat the common mode noise, we grounded the conductors of the PC board assembly to the frame ground with multiple grounding points using our onboard contact. And with this, the impedance was reduced and common mode noise was suppressed. And this is basically in review of our previous, or at the beginning example of the PC board. Comparing the measurements of the original spectrum, lower field strengths can be observed through the frequency range, and remarkable effect can be observed at especially over 500 megahertz. A ferrite core would have little to no effect for this frequency range, but as you can see, grounding is very effective for the high frequencies. Next, we attach a ferrite core with 3 turns to target the low frequencies range. With this, we are able to meet the regulations limit throughout the specific frequencies of 30 megahertz to 1 gigahertz. The effects of using a combination of the ferrite core for low frequency range and grounding for high frequency range, we were able to achieve broadband suppressions.
So we're actually going to talk a little bit about servo amplifiers and how to attach ferrites onto those. This is an added section from our R&D team. So as an example, we'll discuss about best practices when applying ferrites onto servo systems, in this case, more specifically, servo amps. As you may know, servo motors are controlled by the voltage from the PWM controller's pulse signal. And this wave consists of many harmonic frequency elements, and these powerful high frequency signals sometimes generate disturbance noise. So we'll look at the noise propagation path in this configuration. In this system, there are three types of cables: the motor power line, the encoder line, and the power input line. The power device within the servo amp is the noise source, and the noise travels through each cable and radiates out. The noise radiating from each of these cables was isolated and measured, and the noise levels results are shown in these three charts. It was found that the noise emission from the motor power line was the highest among the three cables. So we'll focus on the motor power line and how different solution methods can help to reduce noise. First, we identified two types of common mode current flowing on the motor power line. For the common mode current measurement, a high quality, high frequency current probe was used, as shown in the photograph here in the middle. The motor power line consists of a three-phase line, the UVW 3-wire, and a ground line, E. In this example, there are two common mode currents flowing on the motor power line. Common mode number 1 flows along the UVW and E lines and returns through the air or the reference ground. Common mode 2 flows through the motor power line and returns through the E line or the ground line. Each of the noise current levels was measured and the results are shown in the graphs. The top graph is the common mode number 1 and the bottom graph is common mode number 2. The ferrite was applied in two ways on the motor power line and measured for its effectiveness. The selective ferrite core happens to be our KRFC series core, which is formulated to filter noise around 100 megahertz. The left graph shows the test results in red when the core was applied over the UVW line to filter common mode number 2. And as expected, there's effective suppression around 50 to 65 megahertz, but with a little effect along other frequencies. The right graph shows the test results in red also, when the core was applied over all the lines to filter common mode number 1. This graph shows that it's most effective at 90 megahertz with marginal suppression at other frequencies. In this instance, where there are two common mode currents occurring on the same motor power line, two ferrite cores are required to filter both noise currents. One ferrite placed on the UVW line to filter common mode number 2 noise, and another ferrite is placed on the UVW and E lines together to filter common mode number 1 noise. With two ferrite cores applied over the cable, each one to tackle a different common mode noise, the noise suppression can be achieved up to 150 megahertz. To obtain the best results, identify the noise path with a radio frequency probe, and then apply the ferrite cores in accordance to the current mode requiring suppression. Next, the best location of the ferrite on the cable will be discussed. Overall, the radiated noise levels from the motor power line is shown in the lower right graph. We'll focus on the three frequencies, 40 megahertz, 50 megahertz, and 90 megahertz, with the highest current distribution along the cable. The graph in the middle right are the current distribution along the 2-meter cable. You'll notice that the x-axis shown in centimeters, and for 40 and 50 megahertz, the current distribution is highest around 100 centimeters. At 90 megahertz, it is higher at 0 and 200 centimeters. Since the cable is 2 meters or 200 centimeters, it can be said that 40 megahertz and 50 megahertz resonate near half the wavelength, and 90 megahertz resonates near one wavelength. Next, we'll cover how the location of the ferrite along the cable can affect radiated noise due to differences in intensity distribution of common mode current. Specifically, we'll focus on 90 megahertz, which resonates one complete wavelength along the cable. The chart on the far right shows radiated noise with the ferrite applied near the servo amp, so the antinode of the current, and near the center is the node of the wave. When the ferrite is applied near the servo amp, about 25 centimeters, where the current intensity is highest, there is a dramatic suppression of that radiated noise. However, when the core is applied at the center of the cable at 100 centimeters, where the current distribution is lowest, there is little noise suppression. So this is a simple example, but it's important to consider the location where the ferrite is installed to have the best suppression effect. So in this next example, a metal sheet is added, as shown in the diagram, where the cable is directly next to the metal. So notice in the top graph, the amount of radiated noise was reduced overall. This is an indication that adding a metal plate generally suppresses radiated noise. However, the bottom graph shows an overall increase in common mode current. The likely cause is because the common mode pathway changed and the impedance of the entire path decreased. In the presence of a nearby metal plate, the common mode return path flows through the metal, which reduces the magnetic field. And as a result, even if the current increases, the radiated noise is suppressed. In this example, a distance of 20 centimeters is placed between the power line and the metal plate. And as you can see in the configuration, 60 megahertz and above shows radiated noise increase. When the power cable is closer to the metal sheet, it is easier to suppress radiated noise. Next, this example is when the servo amp and servo motor is ground to separate metal plates. Common mode current returns to each metal plate. While the presence of the metal sheet reduces impedance, since they're not connected, common mode current increases. In turn, radiated noise is significantly increased as the return path is through the air. So what will happen if the two separate ground planes are connected? So here we'll examine how the ground wire connected to the two metal plates affects radiated noise. This is an important consideration for higher frequencies. The thin, narrow ground wire or pigtail wire connecting the two metal chassis has high impedance. Because of this, the connection between the plates is poor, which causes radiated noise or no improvement in radiated noise. When a lower impedance braided wire is used instead, there's a major improvement in radiated noise. So now a cable shield is added to the system, and we'll see how the shield's grounding mechanism affects suppressed noise. In the top diagram, a cable shield is added without any grounding. The shielding effect with and without shield is marginally different. In the bottom diagram, the shield is grounded with thin pigtail wires. The shielding effect among the three, so no shield, with shield but no ground, and with shield with pigtail ground, are still not so different. This is because common mode current, especially those for the higher frequency range, around 200 megahertz and above, is still being allowed to return through the air due to high impedance of the wires. In order to reduce ground impedance, a short, wide ground at both ends of the cable shield is recommended. This includes metal clamps that allow for metal-to-metal contact. And this allows for common mode current to return in a smaller magnetic field and to help significantly suppress radiated noise. So here is a general conclusion. So the best approach to tackle noise is to find its propagation path. Definitely using a high frequency current probe and the common mode current flows towards lower impedance paths. When a ferrite core is applied to the cable, the core's location, the cable can change the effectiveness, and it's exactly what Lynn was talking about earlier. So when common mode current resonates on the cable, ferrite placed on the antinode of the noise effectively suppresses the problematic noise, and it would not work as well for the nodes of the frequency. So an efficient return path of common mode current reduces radiated noise. So return current is prevented from flowing on a large loop and back to the noise source in order to achieve that sufficient suppression. And shielded cable requires grounding with a lowest impedance at both ends. And this is actually mentioned in our other EMC seminar, but it's also reiterated here. So grounding on both ends using a really wide grounding method is the best way.
Yep, I think that's conclude the presentations that we have. Any questions?
Yeah, please unmute your microphone if you have any questions, or you can also use the chat window to type your question in.
Or if there's any slide that you would like us to go back and discuss a little more, we can also do that as well. Yeah, I think in general, basically, overall, what we wanted to really share is that, for filterings, it's mainly kind of to choose the right materials of the ferrite. Oh, there's actually questions.
Yeah, can you look in the chat window? There's a question from Kevin. Or I can read it. I can read it.
I'm happy to explain it more too if it's not clear.
Yeah.
So let's see. How do you expect bundle shielding to compare individual wire shielding and AC versus DC applications? Let's see, that actually would kind of refer back to our other EMC seminar, but generally it really depends on the system. We've seen it where if you bundle too many cables inside the same shield, sometimes they all interact with each other and they might cause some immunity noise issues internally inside of the shield. But it also depends on the feasibility of being able to shield each individual wire or cable separately from each other. Definitely, if you're able to put some distance in between the cables, it's maybe the cheapest and most effective way. We know that's not always possible. In terms of AC and DC applications, let me check with Yumi-san real quick. I'll be right back.
Yeah, in the meantime, if there are other questions, feel free to, put on the chat. We can answer after Kyoko got some feedback from Mr. Yumi.
Hello.
Hello, Akio.
Can we have a copy of slide?
Yes, I think we already forwarded to Candace and Scott before, but I think we are recorded and it will be uploaded onto YouTube. So would that help?
Yeah, I don't recall if I got a copy of the slides.
Okay.
Do you call that? If not, maybe you forward it to me.
Okay. Yeah, I can definitely resend it over. But the presentations, the slide that we will send over will not have the applications photo. And basically those we can show it over, you know, the presentations, but not to share, you know, online.
That's fine. That's fine.
Yep.
We have the presentation.
Okay, good.
Yeah. And that one I think is okay to use, the one that we sent over last time.
Okay, so I'm back. After talking with Yumi-san, he's not sure if there's a situation where the AC and DC would be really close to each other. They should be separate anyway. But generally, the more concerning one is the AC. And that one definitely should be shielded and grounded really well. DC is not necessarily the noise source or noise issue as a general comment. So that might not be the one of concern, but the AC one might be one that you want to take a look at a little bit closer. Let's see.
Yeah, there's some addition to that questions, I believe.
For example, with the servo motor and 2 ferrites, which we expect is a single ferrite placed on each line UVW. Let me see. Lynn, are you able to flip back to that slide?
Yeah, so let me see if I could get it from, is this the one? I think this is where we talk about that it will be
Yeah,
yeah.
that's the one that was prompting my question. Thank you.
Okay, so let's see, I believe, so 1 ferrite is placed on the UVW line to filter common mode 2. Okay, so if it's separate, so if you apply UVW, the ferrite core onto the UVW line, and then another one separate on the E line, it would actually filter common mode number 2 noise twice. It could also work for common mode number 1. Let's see, the other slide, Lynn, I think you had shown earlier. Let's see. This is going to be. Let's see, I believe it's around slide 35 or so.
I see. I think we have a different number. So do you know that?
My goodness. Let's see. It's the one where we're using the current probe to identify the current noise.
Okay.
Identifying noise current with
one.
probe number 2.
This one, right?
No, like all the way back in the beginning of the towards the beginning of the seminar.
Yeah, I think it was the example where in production it was unreasonable to reverse the direction of the one line, and so the conclusion was to put a separate ferrite on each line.
Yes, that one, closer to that one. I don't have the printed version here, but yeah. A little further up. You know what, that one will work. Slide 39, I believe, if I'm not mistaken. Yeah, this one is definitely filtering just that a single type of common mode noise. Actually have Yumi-san in the same room with me now, so let me double check here.
Okay. I can address Alberto's questions next after Kyoko checks with Mr. Yumi so that we can have a clear answer for Kevin.
I apologize. I'm going to try to translate his information here. So what he's saying is that you could definitely put it on the UVW and the E-line separately. There is going to be some improvement in the suppression, but it's not going to be this huge drastic improvement. So it's basically, as long as the space, you have space to allow for that, and it might be similar to the effect of putting in a much larger ferrite core onto the cable instead of smaller cores.
Okay, do you want to take a look at if that answers the question, take a look at the chat window and go to the next question.
Yep. Yeah. So the next question is actually from Alberto. He was asking how low of a frequencies can we attenuate? How many dB can we expect at around 250 kilohertz? So let me go back to this slide where I had overall range of the Y selections of the ferrite core. So for the ferrite, for the filtering part, it's usually the frequency is go from 150 kilohertz all the way to 1 gigahertz. That's where the ferrite materials will work in this range. So at around 250 kilohertz, you definitely is to select the right low frequencies material of the core to target that frequencies. And in general, ferrite core are in the single digits dB. So usually it's get around minimum of a 3 dB, or you can get as high as a 10 dB. But if you need anything more than 10 dB, usually we will recommend it to get selected for the shooting material, which is something of the cable shooting material that has a better of the attenuations, to help combating the EMI noise. Yep.
Any more questions?
I have one question.
Okay.
So as the ferrites get heated, will the temperature degrade the performance?
The temperatures of from the ferrite core itself?
Yes.
And
that is one. And how about the external temperature effects also?
Yeah, so usually, all the ferrite core, it will saturate it if it would go pretty high temperature. And most of the time, the ferrite itself, we, at least on our part, I think it goes up to 85 or up to 125. But the part that we have actually also designed for automotive, so the highest temperature we can go is up to 125. But if let's say that you have it over in a higher temperature and for a long period of time, that definitely would cause saturations, and also definitely the overheat will cause some of the concerns.
Sorry, just to add and clarify a little bit, that basically we have a kind of upper limit on our ferrites because after a certain point, it gets a little bit too hot for the ferrite to function. So that's why we generally limit it to about 125. We're currently developing those for about 150, but right now we're at 125 as the highest. So it basically stops working a little above that. It doesn't necessarily mean that it's broken. It's just kind of ineffective after a certain amount of a really high temperature. Once it cools down, the performance of the ferrite will come back. It'll return to normal. So I hope that answers that part of the question. In terms of saturation, I guess overheating is a symptom of a saturation. So if you do see it happening, you just want to make sure that saturation is not occurring. It tends to happen more with normal mode filtering. So not as much of a concern for common mode noise filtering. So just kind of FYI on that side.
Okay, thank you.
Sure.
Any more questions?
Okay, well, here's Ron from Grand Rapids with a couple dumb questions, because I'm just a neophyte in EMI, except for my ham radio experiences, of course. But on these slides here, I'm not familiar with the notation L and N. You know, when you were showing the slide just a few minutes ago there, L for the wires, what does L stand for? What does N stand for? I'd want to say a line and a neutral, but yeah.
Yes, that's correct. So live, neutral, and ground.
Okay, all right, okay, all right.
Yeah, we make it short.
Yeah, and then LISN is what?
It's the listen device.
Yeah.
Line impedance stabilization network.
Yeah. Okay.
The full name of it.
Oh, okay. And EUT, I would try to think of device under test, but EUT or what?
Same.
Equipment under test.
Equipment. Yeah. Okay. All right. Just the dumb questions there. But
sorry. We should have clarified. Thank you.
Yep.
Any more questions? Okay, not hearing any. I'm going to read a letter prepared by our awards chair, Jim Woodyard. Dear KGS team, since we had 3 participants, on behalf of the Southeastern Michigan EMC Society Chapter 8, I wish to express appreciation for your presentation to our chapter on August the 19th, 2021, entitled EMI Fundamentals and EMC Filtering. The chapter has recognized your professional commitment to the education of our members with a speaker award, which includes a donation in your company's name to the IEEE EMC Society President's Memorial Scholarship Fund. Your company name, topic, and presentation and donation may be viewed at the chapter's speaker award list on our website, along with a complete list of awards given to speakers since 2012. And I'm going to send an electronic copy of this letter out to you in the near future. Okay, next, for those that are stuck through the meeting, I generated a random number list using Google today, and we're going to give out 3 Amazon gift cards provided by KGS, our sponsor and presenter this evening. So the first one will be for $25, and again, you must be present to win, so I'll do that at this time. The first random number was 34, and 34 is John Nance, and I don't believe he is present. Second one is number 5, Mr. Brum, and I believe he is not present. Mr. Brum, going once, going twice. Third number is number 16, Mr. Feng, F-E-N-G. Mr. Feng, are you present? Okay, the next random number was 35. Arnie Nielsen, Arnie, are you present? Next random number was 46. 46 is Barry Stelz. Barry, are you present? This can take a while. Next random number is 50. Mr. Tang, are you present? Next number is number 1, Mr. Agarwal. I did not see him. Next one, number 10, which is disqualified because it is KGS. Sorry, Lynn.
Oh no.
Sorry, Lynn. But congratulations anyway.
Thank you.
Next one was number 33. Otto Mueller, not present. Boy, this is pretty crazy. Next one is number 22, Ken Haddad. Ken, are you still here? I checked Ken's name off. Ken Haddad, are you still on
the meeting?
Yeah, I see him too.
Ken?
Here, yeah.
Oh, okay. Ken Haddad.
He's
Ken,
muted.
you just won a $25 gift card from Amazon. Let me verify your email address, khaddad3@comcast.net. Is that correct? Ken? Hey, Ken, can you unmute your mic? Ken? I thought I heard him. Ken, Ken, are you still here? Ken? Was that Ken talking before?
No, sorry, that was me. I was saying he's in attendance, but he was muted. Maybe he's plugging in his microphone right now.
Okay.
Yeah, Scott, you can see he just unmuted, so he just can't speak yet.
Okay. Well, we'll move on. Maybe he's having an equipment problem there. So $25 went out to Ken Haddad. Next lucky number was 13. 13 is Hung Do. Mr. Do, are you still online? If so, unmute your microphone, please. Mr. Do, I don't see him up here anymore. Okay. Last chance, Mr. Do. Okay, moving right along, number 57. Ito Atsu. Ito, are you here?
Yeah, I'm here, but I'm from KJS.
Oh, okay, you're disqualified.
Wow.
Okay, sorry about that. Next number was 17. Michael Flugeman.
I'm here.
Okay, hey, Michael.
Hello.
Okay, excellent. So Michael, you won the $50 gift. Congratulations.
Well, thank you.
You're welcome. Next, then the grand prize is coming up next. So that is for $75 gift card, number 27. Oh, it's me, but I will not take it. Scott Lytle. Next one is number 44. Sarav Sresra. Sorry, he's not present though. Next lucky number is 3, Tom Baruki. Or Siki.
Here, thank you.
Say your last name for me.
Baruki, that was pretty good.
Baruki. All right. So let me verify your email, thomas.borucki@gm.com.
Yeah, that sounds good. Thank you.
Okay. And Michael's, yours was eaglescoutmdf@gmail.com.
That's correct.
Okay. Well, we had to go through quite a few numbers tonight, but we got it done. Okay, I'm going to stop the recording at this time. And if you would like, you can hang out here and continue to visit if you like. So I'm looking for the stop button. Here it is. Okay.